This is Module 8, Lecture 2 in the book Problem-Solving Guide for Electromagnetism and Optics, Source of the Magnetic Field. Here we are going to be adding magnetic field vectors and calculating where the magnetic field is 0. And here we are looking head-on at wires. There's a long wire carrying a current of 200 milliamps directly into the page at the point 1 centimeter, 2 centimeters. So 1 centimeter in the X, 2 centimeters in the Y. There's a wire that's going out of the page and into the page. It pierces the page at the point 1, 2. And it's carrying the current into. So these is like parallel wires. This wire is carrying the current into the page. This wire is carrying current out of the page. And they go long in both directions. This wire is 300 milliamps at -2 +2. What is the magnetic field at the point 1 centimeter 0? That's right here. What's the magnetic field here produced by these wires? Both of these wires make magnetic fields circles around the wire. You have to figure out if they're clockwise or counterclockwise. Part B is, where is the magnetic field 0? Let's address part A first. To get the magnetic field at this point, we need the vector contributions to the field at that point from each wire. And then we have to add up those vectors. So that's wire 1, that's wire 2. Now we got to get the directions. To do that, we're going to start by drawing lines from the wire to the point where we're measuring the field, like that. Since the field is a circle around the wire, the magnetic field direction is going to be perpendicular to these radii. So B1, this is out of the page. If I point my thumb out of the page and curl, I can see B1 is in that direction. That is a right angle. This is tangent to the circle around this point. This guy, I have to point my thumb into the page. So he's directly to the left, making a field directly to the left. That's B2. The magnetic field at this point is the vector sum of these two fields. Using the Pythagorean theorem, we can get the distance. So 2 squared plus 3 squared, square root, that's 3.606. So this distance is 3.606 centimeters, and this one is clearly 2 centimeters away. So now we can calculate how long this vector is, the magnitude of the vector. So mu naught I over 4 pi a, perpendicular distance. That is the perpendicular distance. And 2 is because it goes infinite into the page and infinite out of the page. We can plug in the numbers, push the buttons, 1.66 microtesla. Now we can address the field from wire 2. It's got a perpendicular distance of 2 centimeters. Converting that to meters, that's the current in wire 2, 0.2 amps, 200 milliamps. There's mu naught. This wire is also double infinite into the page and out of the page. Crunching the numbers there, I get 2 microtesla. These are vectors, of course. We have to add them like vectors. We have to break down B1 into the X component and the Y component. To do this, we need the angle. What's this angle here? Well, it's arctangent of 3 halves. This angle here is the same. Opposite side is 3, adjacent side is 2. That's 56.31 degrees. Now we can calculate the horizontal component, 0.923. That's this guy. And 1.38 is vertical. To get the net horizontal component, we got B1 this way, B2 that way. B2 is -2, is 2 microtesla to the left, and we get minus 1.068. So the net magnetic field minus 1.068 this way, and B1's easy, or the vertical component's easy, it's just from B1. So that's 1.38 microtesla straight up. So now we have this, 1.07 microtesla this way, 1.38 microtesla that way. We can use the Pythagorean theorem to get the magnitude. B is the square root of B sub x squared plus B sub y squared. So this vector, 1.75 microtesla, and we can use arctangent to get the angle, 52.4 degrees. So the answer is 1.75 microtesla at 52.4 degrees above the negative x-axis, and we can draw a little diagram right here. That's the answer to part A. Now we have to determine where the magnetic field is 0. The magnetic field's only going to be 0 when the two vectors are equal in magnitude and opposite in direction. This wire is 300 milliamps. This wire is 200 milliamps. So this wire, you have to be closer to this wire than this wire, because this wire has a smaller current. In between, the fields are both up. If you point your finger out of the page and curl your fingers around, in between, it's going up. If you point your finger into the page, the thumb, for this wire, in between, it's also going up. There's no way there can be 0 magnetic field here, because both of these wires produce a magnetic field upward. The only region that can possibly have a magnetic field of 0 is to the right of this charge. So this wire, put your thumb into the page, it produces a field down. This wire, wire 1, produces a field out of the page, up here. So this wire produces a field up. This wire produces a field down. At some distance, they're going to have equal magnitudes. Somewhere over here, some distance x. So here's the B from wire 1, it's up. Here's the B from wire 2, it's down. So the magnitude of the field from wire 2, it's x away. This point is x plus 1 centimeter, but this wire is x away. So there's the formula. Mu naught I over 4 pi times the perpendicular distance, which is in this case is x. And this 2 is because it's double infinite. It goes into the page and out of the page. From wire 1, the distance between this wire and the point where we're measuring the field is x plus 3 centimeters. And that's what's in the denominator here. This wire carries a current of 0.3 amps. It is also double infinite. If I set these magnitudes equal, I can calculate x. It's a big hairy equation, but a lot of stuff cancels. Get rid of the 4 pi, get rid of the mu naught, get rid of the 2's, get rid of the amps, and it looks like that. So now we cross multiply, and we distribute the 0.2, and group the x terms, and we get that x is 6 centimeters. So this distance is 6 centimeters. Don't mess up now, you're almost there. The point at which the field is 0 is 7 centimeters in the x direction, and then up 2 centimeters in the y direction. 7, 2. Now, get to work, do a lot of problems.